Hey guys. Oh, I think we're live. I think it's working. Let's see. What do we got? Is it here? Nobody here. Oh, yep. Okay, it's working now. I'm actually getting the hang of this. Let's see. Anyone in? Not yet. Participants. Anyone who's here, go get the others. Oh, you're here. Hey guys. Cool. Right, I better put the question up that I want you to start on. So, Jules, what we're doing is we're doing parametric differentiation, and you'll know how to do it from scholarship last year, but you won't have the textbook, which is kind of a pain. Can you, if you want to do a month of A-level maths with us, maybe if you send me an email and I can try and help out with the textbook. Right. Okay, so there's a question I want to start off on while I go and make a coffee, and also we've just got our bread maker going again, so there is a loaf of bread just appeared in front of me. So while I'm doing that, I want you to start with this one, and we're starting with this because your homework was to read ahead in the book. All right, so you had those pages 104 or something to read. So this is my curve, and it's defined as a parametric thing. So this is really cool seeing people from other schools. So well done, guys. Lovely to see you. If there's anyone else out there lurking, please come on and say hello. My Year 12s are really nice and they won't be mean because I'll get mad. Hey, Ben. It's nice to have Ben Hong here. That's going to make for at least 2 Bens on the live chat. So getting back to the maths, this is my curve, right? And it's really, really hard to visualize this. But one of the reasons that parametric equations are so cool is they let us trace out all kinds of weird and wonderful shapes. And if we were in class, and if I'd had more time to plan this, I'd show you even more cool curves. But you can do like stuff like this, right? Parametric equations let us do not just functions, but relations. And you can draw lots of lovely pictures. So I'll have a look for some of that in the drive to see what I can find. But typically a parametric question goes like this. You're given x equals something and you're given y equals something, right? And the classic first step is that you have to find the gradient. So we know that this is going to trace out some shape, right? So where's my pen gone? Oh, my pen stopped working. Well, there we are, pen's working. So we're going to trace out some shape. Maybe it looks like that. We have no clue, right? And we need to be able to find the gradient at any point on the curve. So the first thing I want you to do with this curve is to find dy by dx. And then I want you to tell me for what values of theta is the tangent to the curve parallel to the y-axis. Okay, and then the extension question is to try and find, and I haven't taught you this, but some of you have probably worked out how to do it. Jules, you'll know how to do this from last year, so don't blab, right? I want to teach this. I want you to find the second derivative, because as you know, we always need the second derivative to show whether something's a minimum or a maximum. Okay? Right, I'm going to go and cut the loaf of bread and put some Marmite on it and make a latte. If you finish that, don't finish that. I'll be back soon. hello. Crystal speaking. Hi, you live on my live stream. Shall I put you on speaker? Miss Rules is here, everyone. Actually, she's on the phone. No, I'm actually making a coffee and some toast while they do some work. Oh. What's that? Oh, you're outside the house. Oh. You're allowed to come in today, as long as you stay 2 metres apart. Oh, so we need to bring the stuff out. Hang on. Let me just go and get Tim and the kids to do it. Hang on. I'll just tell the boys. Right. I've just got a year 10 from Mount Albert Graham has come on to my A-level. Hey, Jules, you are a different Jules. Right, I'm going to go and find someone. Guys, sorry, I'm talking to you and I'm talking to them at the same time. Right, boys, I'm going to be 5 minutes. I have to get a whole pile of Lego into someone's car, okay? So just keep going on the question and then have a look at the textbook. Just a sec. I'll find some. Where is it? Are you right outside? Right, he's on. Is it? Okay, I'll go get kids to help. I'm having such a fun afternoon. Yeah, good day. Good.
Are we taking the chair?
You're taking her, not the chair. She's not going to chair. What's that? Yeah, I'm getting into this window. I'm definitely tired today, and I managed to go for a run, so that's good. Okay, Fletcher's bringing it all up now. I'm going to go back and do maths. But yeah, good luck. Bye. Right, guys. Sorry, I'm back. Okay, Jules, the reason that's really funny that you're not the one I thought is that we had a Jules who came to scholarship last year from another school. So, yeah, you're very welcome. Come on in. And yeah, can you send me an email so I can put you on the email list? Yeah, that's really funny. Okay, so what have we got? Well, we have to differentiate with respect to theta. Just let me find my bit of paper. Sorry about that. We are lending a whole pile of kids' toys to Miss Rules for the next month. So she's just in the car outside. But that's okay. Right, so we get dx by d theta. Yeah, Cam, you're nearly right, but you're not quite right. So dx by d theta is going to be this. It's going to be 3 cos squared theta times negative sine theta. Right? And dy by d theta is going to be, we have to differentiate this, right? So it's going to be 2 sine 2 theta. So you've got to have the 2 because you're doing a chain rule on this one. Okay, so Cam, that's what your mistake is almost certainly going to be. Now, the next step is how to get dy by dx, right? So this is telling me that when theta changes by a little bit, what happens to x? And this is telling me when theta changes by a little bit, what happens to y? What we want to know is when x changes, how does y change? And the reason we want to know that is because we've got a curve, right? And so we're saying what happens as I move around the curve from one x value to another. So we want to know dy by dx, and we use the chain rule to get there. We get dy by d theta times d theta by dx. Okay, hi Jules Webb. Are you Jules or Jules? Because our Jules is French. Well, he's half French, and so that's why I've been saying Jules and not Jules. So now we all want to know that, so you have to tell us. Okay, so dy by d theta is 2 sine 2 theta. Did you take all of the stuff out, Fletch?
Yes, I did.
No, there's all the books.
Oh,
Don't let her go. Sorry, guys, I'll be back.
I thought it was just Lego.
No.
Sorry. I had no idea. I had no idea.
What did you do?
Alright guys, my mother will be back at some point. Yeah, I wish I had Lego right now too, but it's gone, George. It's all gone.
Who's George?
Guys, okay?
Yeah.
Can I carry it all out? Come on. Okay.
Who's George?
George is Katie's son.
No, the
No, not the other George. The legendary George.
So can this all go?
Yep. Shoot.
Sorry guys, I'm back. Are you doing maths? What did you do? What did she do? Oh, maths joke. Okay guys, hey, I'm really sorry about that. But Miss Rules was here and we had half a house full of Lego and toys to give to her for her 2 little kids. So that's what that was all about. I'm going to make sure Teresa doesn't come back for the next month. Otherwise, you're going to not come on my live streams because the jokes are so bad. Hey, we've got a dislike now, guys. Oh, it's probably... I hope it's not in the class. Okay, I'm back. Let's do some maths. Right, off you go. Go downstairs.
Don't erase it.
Right, off you go. Go away.
That's a golden joke.
It is.
No,
It's great.
stop
Can you just
erasing
go? Okay. So,
Bye.
what we've got to do now is we've got a chain rule. Okay, so we've got this, 2 sine 2 theta times the reciprocal of this one. All right, so it's going to be times 1 over negative 3 sine theta cos squared theta. And you don't have to write it out as 1 over for long. You'll pretty quickly get the hang of this. Something's not right. Where am I getting... Oh, no, that's right. And now we're going to do the sine 2 theta. So, sine 2 theta is 2 sine theta cos theta. So we get 4 sine theta cos theta. I'm going to move my negative sign up here over 3 sine theta cos squared theta. So that gives me negative 4 over 3 cos theta, which is a perfectly decent way to write it. And that gives me, written with the reciprocal function, negative 4/3 sec theta. Okay? Right, so that's the first part of the question done, and that's your basic approach to parametric differentiation. And this is about a merit level 3 question already. So if you get the hang of parametric, it's really, really great, because often the second derivative is excellence level 3. And once you've got the hang of that, it's super easy. So the next thing we have to say is, for what values of theta is the tangent to the curve parallel to the y-axis? So what do I now have to do with this to find where it's parallel to the y-axis? Type in what we have to do into the chat. Okay, I'm seeing all of your stuff. Right, I'm just seeing all of these questions. So type in what you've got for how do we do the next bit. Okay, Cam, I'm going to come back and go over how we differentiate, all right? Yeah, it's fine, guys. You can pop in and pop out, all good. Right, so what am I doing when I figure out for what values the tangent to the curve is parallel? So parallel to the y-axis, how do we do it? No, the gradient is 0. Think about it. Parallel to the x-axis means the gradient is 0. Parallel to the y-axis, we want the gradient is undefined. Okay, so the gradient's going to be undefined when the bottom line of the fraction is 0. Yeah, that's why I like this question, Jamie, because we don't think about parallel to the y-axis as much as parallel to the x-axis. Okay? So parallel to the y-axis means dy by dx undefined, or infinite, if you want to think of it like that. So let's look at what dy by dx is. dy by dx is negative 4/3 over cos theta. So we need to have, that's right, Havisha, we need to have 3 cos theta is equal to 0. So this is one of those times when we sketch our cosine curve. So Jules, hopefully you've been told always draw stuff. So Cam, it's not going to be tan theta is equal to 0, it's going to be cos theta is equal to 0. Right? We need to have 3 cos theta equals 0. When will that happen? Well, we've got pi on 2, 3 pi on 2, 5 pi on 2, and so on. But what we typically find with these functions is that, a bit like we have with when we do polar form or for complex numbers, we get repeats after cycles of 2 pi, and it's the same thing here. Okay, so that's right. So we're solving cos theta is equal to 0. So it's parallel to the y-axis for these values here. Right? So that's the first part of that problem done. I just want to show you what the curve looks like in Geogebra. And I've put it in here. No, that's the wrong one. Oh, now I'm giving away my other ones. Not that one, this one here. Right, so this is a screenshot now of x equals cos cubed theta and y equals 1 minus cos 2 theta. Right? So as we move theta, the x and the y change. Now I'm going to go into Geogebra. Hopefully this will work live and just show you what happens when we move the thing. Just looking for attention. Okay, so what we're going to look at is what happens when we move theta, right? And when we move theta, t will change. So if we have a point on the curve, hopefully you can see this okay, but that point on there is changing. So see how I'm moving point A with the mouse? Well, what that means is that the x value and the y value are changing. But I don't know if you can see that in the window down here or not. So if we look at the value of t here, no, it's not going to work. I'd like to be able to put a slider in there that shows you, but what you can see happening is that the slope is undefined at the following places. Up here, you can see the slope gets goes to infinity, right? And then down here, right, the t value or the theta value is changing everywhere. So the command that I want you to learn how to use and go into Geogebra and do, but not now, is this one here. So you have to have, you go to geogebra.org, and then you need to have what's called the classic version of the app, right? And when you've got the classic version of the app, there's a command that you can use that goes like this. So it's got syntax like this. It's curve, and then you type in cos cubed t, 1 minus cos 2t, and then you give your parameter, and then you give your values that t varies from. And I think whenever you're doing parametric problems, it makes much more sense if you have a picture of the graph in front of you, because it means that you can visualize what you're doing with gradients. Okay, so that's what I'd like you to do after this lesson. So between today and tomorrow, go and download Geogebra, get the classic version, and then play around with some of the examples in exercise 4E. So that's the first one that I wanted to look at. Now there's another one that I want to do, which is from the exercise. Guys, can you just tell me how many of you started to do 4E? How far did you get with 4E? Just type in so I can see. If you didn't get anywhere, tell me that as well. Okay, I didn't think that you would have had time to do 4E, so that's fine. But I want you to do 30 minutes on 4E tonight, and I'm going to pick out a couple of the exam questions to do now. But you do need to do practice at this, guys, or you won't build up your fluency. Okay, who else is here? Right, good to see lots of you here who weren't here the other day. Yep, it's quite a big exercise too. So what I'm going to do now is I'm going to pull out a couple of questions and go a little bit further with them than the book does as well. Right, so this is the one that I want to look at first. So question 14 has got the following curves. It's got x equals 1 minus e to the negative t, and it's got y is equal to e to the t plus e to the negative t. I'm going to spend the rest of this live stream probably looking at what we're doing. Thanks, Michael. Yeah, that's good, but yesterday it didn't show you up as being there. So I think it's only if you've actually spoken that you come up. I'm not sure. Yeah. So I'm curious, is Jules, are you still here? Because you're not showing up in that chat window anymore. Yeah. So all good if you need to leave, by the way. It's fine. These are not compulsory, but I think they're going to help. So the first thing I want to talk about is how do I figure out what this curve looks like? Because sometimes we can take the x and y and we can put it back together into a normal curve. And the way that we might do that is by trying to make t the subject, right? So we can do a whole lot with it in parametric form, but let's try and do making t the subject. So you can do this with me if, as I go. I'll do it on the screen, but you should do it on a piece of paper, and then we'll go back over it. So I get e to the negative t is equal to 1 minus x. Then I'm going to take logs of both sides. And I get negative t is equal to the natural log of 1 minus x, which gives me t is equal to negative log of 1 minus x. Using my log rules, that gives me t is equal to the log of 1 minus x to the power of negative 1. So t is equal to the log of 1 over 1 minus x. Okay? So that's useful because I've now got an explicit expression for t. What can I do with that? Then I go up here and I plug this in. Right, Cam, Bobby and Michael, that's all good, but can you make sure that you're doing the maths with me, right? So we're making t the subject. So we've taken one version where it's easy to see from looking that we can easily get t as the subject here. Here it might be trickier. Okay, so the next thing that I can do is to say that y is equal to e to the power of t plus e to the negative t. So y is equal to e to the power of this, the log of 1 over 1 minus x plus e to the negative log of 1 over 1 minus x. So moving through this and recognising that e and the natural log function are inverses of each other, this gives me 1 over 1 minus x. Now I'm being pretty fast and loose with domains and ranges in here, guys. Now this is one where we've got to really watch what's going on, and we'll come across this situation when we do differential equations later. But it's really tempting to think this is easy because I've got e to the power of negative log. We have to rewrite it like this or we get into a big mess. this negative, we've got to think of putting it back inside the log. So this is the log of this to the power of negative 1. I'm working very slowly here. 1 over 1 minus x plus e to the log of, and we're back with 1 minus x. Right, so now we're down to this. Y is equal to 1 over 1 minus x plus 1 minus x. So what we've done is that we've gone from this parametrically defined curve, right? Let me just get that back up. Right, just cleaning that up a tiny bit. Right, this is my curve in parametric form. Incredibly useful because as I change t, I change x and I change y. So that's really good, except that it's really hard to visualize what it looks like. So by doing this thing where I've made t the subject, I've managed to get it back into a normal Cartesian plane curve. So I guess what I wanted to know when I've done this is, what does it look like? And does it look exactly the same as in Geogebra? Right, so in Geogebra, I first put this in like this, curve 1 minus x negative t. I'm just showing you the syntax to get you used to it, right? Because it's a little bit funny. And then my parameter's t, and I can't remember what I did. I think I did negative 100 to 100 or something silly like that. So that drew me a curve. And then I went and I just drew that equation in Geogebra. And the thing that I want to have a look at, and this isn't really for an exam question, but it's for your understanding of functions and relations, is that the two curves don't look exactly the same. So this one is this version, and this one can have negative y values. The only restriction on that curve, as I've written it, is that x can't equal 1. But x can equal anything else. But for the parametric one, it doesn't draw me both branches. So I'll show you what I'm talking about so it makes more sense. Right, this is what I get if I type into Geogebra y equals 1 minus x plus 1 over 1 minus x. You can see that it's perfectly possible to get negative values of y, right? So you can generate that whole branch. You just have got an asymptote sitting in here, right, for pretty obvious reasons that you can't put x equals 1 in there. But if I draw the parametric equations, this is what I get. I just get that top branch. So if we look at the form of the y equation, I want you to tell me why am I only getting the top branch, right? So there's my parametric version. I just thought this was a nice thing to fall out, right? So there's my x, and there's my y. So type into the chat, why have I only got half of the graph when I'm doing the parametric form? Right, let's see what you're saying. Oh, this is awesome, right, guys? Nice answers. Yeah, y is always positive. That's right. Okay, so hopefully you're starting to get a feel for how cool these parametric things are. But we're not done yet. I've got two more things that I want to show you. So you'll notice that we haven't actually found the gradient yet of this one here. And this is from question 14 in 4E. So let's just see. Who all is here still? Everyone's still here? I think most of you are still here. Yep. Let's see. Okay, yeah, it's not showing everyone up. It definitely is only people who've been talking in chat, guys. So let's differentiate. We've got x equals 1 minus e to the negative t, and y is equal to e to the t plus e to the negative t. So dx by dt is equal to, well, this is 0. Now, this is a negative. Chain rule tells me that's negative 1. So the derivative of the first bit is e to the negative t. dy by dt. Differentiate the first bit and I get e to the t. Differentiate this bit and I get minus e to the negative t. Cam, at the end, remind me and I'll go over your burning question about the trig derivative. Okay? So, what have I got to do now? Well, dy by dx is equal to dy by dt times dt by dx. Now, that's the chain rule written out nicely, but we pretty quickly stopped doing that because we noticed that that means it's this, dy by dt divided by dx by dt. And often you'll see books shorten it like this, and I hate this, but I've kind of started doing it. It's y dash over x dash, and that's perfectly okay notation here, even though I don't like it. Right, so all we've got to do now is go dy by dx is equal to this. It's e to the t minus e to the negative t divided by e to the negative t. Now we're asked to show in the question, we're asked to find an exact value for t where the gradient is 2, right? But we're also asked to show that dy by dx can be written as e to the 2t minus 1. Right, Bobby and Cam, I love that you're doing your trig derivative along the side, but can you get back to doing this question here? Right, so I'm going to give you time now, 2 minutes, to see if you can go from here to here. So just do that in your book, and then I want you to type in, are you green or orange on doing that? So you don't have to type in how you got there, but just tell me, are you green or orange? Michael, you're asking a good question. Why would you need to convert parametric into Cartesian? Because well, sometimes you're going to want to do that to be able to see the curve, right? So it will depend on the situation. Your graphics calculator can put in parametric on some of them, but it's much easier for me, for example, to visualize. So say someone says this, I visualize that straight away. Now we can write that out with in parametric form, and that's fine, but I find it much easier to picture things in this form. It's not just me, it's a good skill to have to be able to go back and forth between parametric and Cartesian. Okay, so Bobby's green, Kieran's green, who else is green so far? Yep, Bobby, just give us all a chance. I didn't, yeah, oh, that's fine that you put that in. You're dead right, but everyone needs to be doing that question. So I just wanted you to go green or orange for that, but that's cool. Right, so what we've got to do here is dy by dx is equal to e to the t minus e to the negative t over e to the negative t. But that negative t down here is equal to e to the t in the numerator. So that gives me e to the 2t minus 1 as required. Now we're asked to show when is the gradient equal to 2. So we're solving 2 equals e to the 2t minus 1. So we get 3 is equal to e to the 2t. We take logs of both sides. The log of 3 is equal to 2t, and so t equals a half log 3. Right, just make sure that you can do this question completely on your own, because it's a really nice little exam question. Remember though, you really won't have much time in the exam, so you've got to have it totally fluent. Now the last thing I want to do with this question is to show you how to do the second derivative. So we've got, where have we got down to? Let's just back up a minute. So in this example with the weird graph, we've got x equals this, and we've got a nice expression for my first derivative, which is e to the 2t minus 1. Whoops, that's not up there. That's this. So we're down to here. So how can I show that something is... No, Kieran, do not leave anything in decimal form. Exact value, okay? Sorry, I just saw Kieran saying, should we put it into decimals? We definitely should leave it in log form. Because, or in this question anyway, it says exact value. But if you're getting as nice an answer as this, just leave it like that. That's an exact answer. Don't go to an approximation. Okay? Right. Suppose that let's now figure out where this point is. Let's just go back. It's not letting me move back. Where's my Geogebra window? Nope. Hang on. Wrong curve. Okay, suppose now that we're going to try and find where that minimum point is. So how can we do that? So find the minimum. And then I'm going to do the next part of the question, which is where we need the second derivative, show that it's a minimum. So as soon as you see this, you should be thinking, I need to be finding the second derivative and showing that the second derivative is positive. So d squared y by dx squared means take my first derivative, and this is the working that you should be showing for this, and differentiate it with respect to x. But we've got a problem, right? Because my first derivative is in terms of t. It's e to the 2t minus 1. So what can I differentiate with respect to? I'm leaving a huge long gap. So what can I differentiate with respect to? I can't differentiate with respect to x, but I can differentiate this with respect to something else and then use the something to finish the problem off. Yes, I can differentiate with respect to t. Well done. So this is what we'll do. We'll differentiate with respect to x, to t, and then we'll use the chain rule to finish the problem off. We know this from up above, and this is going to be easy. Okay, so d squared y by dx squared is going to equal 2e to the power of 2t times dt by dx, which is 1 over e to the negative t. And that gives me 2e to the power of 3t. So that's my second derivative. Now we're going to find out where that minimum is. So we want to solve dy by dx equals 0. Dy by dx is equal to, so we've got e to the 2t minus 1 equals 0. This is going to be really easy, right? E to the 2t is equal to 1. Take logs of both sides. 2t is equal to the natural log of 1, which is just 0. So t is equal to 0. So that was fine. But we want to show that we've found a minimum. So at t equals 0, we now evaluate the second derivative. D squared y by dx squared is equal to 2e to the 0, which is 2, which is greater than 0. So we've found a minimum. Right, so yeah, I think this is pretty cool. I think this is pretty useful as well. So make sure you've got that down. The Cambridge book doesn't do second derivative of parametric, but I think it doesn't make any sense not to do it. This is in Delta somewhere. It's in the differentiation chapters. Just seeing if it's taken anyone out of the chat. No, it hasn't. Cool. Right, I just want to go over the chain rule stuff that Cam was complaining about earlier. Okay, so it says there's 18 people watching. Is Hannah out there? Hannah, if you're out there, come and say hello. I think you're watching, because Mum said you were. And if Hannah's not out there, that's fine too. So yeah, Havisha, they don't do it enough, and it's done, and it's definitely in the extension exercises in Delta. I might, when things get a bit more normal, I might do a few more YouTubes like this with second derivative of this one. But the last thing I want to do is to just go over some really basic trig derivatives. So suppose I've got 2 cos 2 theta is y, right? And then I saw lots of argument about how to differentiate that. Right, so going really slowly on that, that's just y equals 2 cos u, and u is equal to 2 theta. So du by d theta is equal to 2. So when I chain rule this, I've got dy by du is equal to negative 2 sine u. So dy by d theta, dy by dx is equal to dy by du times du by d theta, which is negative 2 sine u times 2. So we get negative 4 sine 2 theta. Now I heard Kieran talking about doing the double angle formula first here. I really, really don't want you doing that because it's just not that efficient. You have to be completely fluent with the chain rule at this level. So Kieran's quite right. You can get there with doing 2 cos 2 theta, but this is how that would go. We can pick any of them, but we might pick, I don't know, 1 minus 2 sine squared theta. Right, so then we've got 2 minus 4 sine squared theta, dy by dx. Is that right? Yeah, dy by dx is going to equal negative 8 sine theta cos theta. Okay, so that's doing it that way, and then recognizing that that equals negative 4 sine 2 theta. So that would be marked correct, that would be marked correct, right? And they're the same. But you can see that it's good. Yeah, you said that it took too long. That's great. Okay, cool. I agree that it takes too long. So we just want you getting good at chain rule. Lots of you are doing quite well with the Education Perfect. I'm just going to go into a really quick check because it is good practice. So go do it. Can I just quickly get some feedback on here? Can you tell me, do we want so we've done trig functions, right? We've done them at a basic level, and now you've got to go away and build up the fluency. But yeah, Kieran, that's right. We've done chain rule and we've done trig functions, so we should be able to do both together. Tomorrow, do you want a live stream? So can you tell me on a scale of 1 to 10, a live stream tomorrow? And I'm quite happy to do them because I'm sensing that you're enjoying it, but I'm also sensing a couple of you probably not. And the thumbs downer, I don't know who that was again. Maybe that was just Teresa's bad joke. So tell me, scale of 1 to 10, do you want a live stream tomorrow? Yeah, cool. No, it's not too much trouble. It's not too much trouble. I thought what we're going to do tomorrow is I think we're going to do a session on trig. Yeah, maybe we do that. How about you do 4E and come into the live chat ready with questions you want done. And then we're going to do a trig section. And I think I'm going to post you some trig identities from Miss Zhang's class. Okay? So we'll have homework time in the morning and we'll do the live stream in the afternoon. And you don't have to do them, right? So if you're a sort of a 6 or below, then just don't come on. That's fine, because I know they take time for you as well as for me. Cool. All right. Well, we might leave it there, and I will post the time, but it'll be after lunch. All right. Cool. Okay, I will catch you guys later on. Have a lovely afternoon and stay home except for going for a solitary walk or a run.